In this video, we're going to discuss functions. Functions are building blocks in C++. You definitely need them, and you'll use them even more when you use classes. When we talk about steps in a process, we often use abstractions. To calculate a square root, for example, we estimate. First, get as close as you can by finding two perfect square roots that your number's in between. Then we divide your number by one of these square roots, and then we take the average of the result of step 2 and the root, and then use the result of step 3 to repeat steps 2 and 3 until you have a number that is accurate enough for you. But in C++, to calculate a square root, we don't do all this, or in English as well. We simply say x equals the square root of y. So, square root is a function. A function is an abstraction encapsulating multiple steps under one easy-to-remember function name. One way to think of a function is as a black box. It takes a parameter, it takes parameters, one or more, it performs something, and then returns some value. Now, what are these terminologies? Parameters are one or more pieces of information we pass into a function. These can be literables, and they can be variables or constants. A function can have 0, 1, or more parameters. There should be a reasonable limit to how many you have, but there's no fixed limit. Return value is the result that the function computes. Some functions return no values and are said to have a return type of void. Functions execute as though they were a textual replacement of their call by the contents of the calling program. The characteristics of a function: functions have 0 or more parameters. All parameters must have a type. A function may return one and only one value of a specific type. A function is named using the same rules for variables. For example, you can't start one with a number. The combination of return type, function name, and parameters is called the function signature or prototype. So let's write our first function. Let's create a simple function to compute the sum of all numbers from 1 to n. According to inductive proof, 1 plus 2 plus etc. up to n equals n times n plus 1 over 2, where n is a positive integer. Our function would therefore take one parameter, n, and return an integer. So our call to the function would look like this. Int sum equals quick sum 25, and this should print out 325. So let's implement this function real quick. Okay, we'll say int, because that's the return type we want, quick sum, which is the name of the function. It's going to take one parameter, int n. Okay. Now, when you comment a function, usually it's good to comment it in some sort of block. Name, quick sum, parameters, and a number we want to sum up to. Okay. And return value. Computing sum. And then generally give it a purpose. Purpose adds the numbers from 1 . Okay, so now we implement it. I'm going to say a return statement equals that equation is, I had to check on that for a second, n times n plus 1 over 2. So we're going to return n times n plus 1 divided by 2. Now to use it, we'd say call the function, pass in a parameter. So now we've got this all set up. And let's run it. And there we go. So we've implemented our first function. Now, if we look at some things here, we've got a statement called return. That's how we indicate the value we're going to return. It usually takes it. If you have a return type that's not void, you have to return something of that type. If you have a return type of void, you can either just do a return with no expression, or you can just let the function complete. Those are usually called procedures. Okay, function name, parameter, function, the function body, that arrow high up, and the function signature is here. So let's look into this again as we enter a number, n, and then the sum of quick sum to 25. We should actually replace this with n. And then here's the actual function implementation. One way to think about this is if we replace the call quick sum 25 with the contents of the quick sum function with the parameters replaced. So quick sum 25 would become sum equals sum plus 25 times 25 plus 1 divided by 2. This isn't really how it works under the covers, but for purposes of illustration, it's a convenient way to think about it. We use functions for abstraction. It's easier to say start car than list all the steps each time. Reuse. We write a function, give it parameters, and reuse it. We avoid writing different code for each use that varies by a few variables. This makes your code easier to maintain and easier to read, too, for code cleanliness. Also, it lets us separate our concerns. Functions can focus on one purpose and one purpose only and not get lost with the jumble of the rest of your program. So here's some good habits. When writing functions, consider these guidelines. Do exactly one thing in a function. Consider future use. Are we going to only use this in this program, or are we going to use it in a different program? That will impact how you package things. Validate your parameters. In other words, make sure they have reasonable values and they don't cause errors. In functions, it's not a great idea to intermingle computation and display. Have a function to compute, have a function to display. Break complex functions into simpler ones that can call each other. Function composition, just like in math, is a good thing. Comment functions like separate entities from your program. In C++, there is a requirement that a function must be declared before it's used. So, parameters are how we pass values into and sometimes out of a function. A function can have 0 or more parameters. The combination of a function name, its parameters, and its return type is called its signature or prototype. Every parameter has at least 2 parts, a name and a type. So, void create point, our name is x and our type is int. X and y are both parameters of type int. The function returns no value. Now we have int sum, int x, int y returns x plus y. X and y are both type int. Function returns a value of type int equal to the sum of x and y. So, there's 2 types of parameters basically. There's value parameters and there's reference by parameters. The default parameter behavior in C++ is passed by value. This means when you call a function f with parameter x, the value supply for x is copied into the parameter x. X is a copy. It's not the same variable. Changing x in the function will not change x outside of the function. The value of x is passed into the function, and it's not a reference to the actual memory. That is called pass by reference, which we will discuss later. So here's an example. We'll skip over and look at it here. Here, when we make our call, we call sample function a comma b. The value for a, which is 1, is copied into x, and b is copied into y. Z equals x plus 1, so z would now equal 2. X equals x plus 1, so x would now equal 2. Y equals a new string, return z. So this will return back z, which should be 2. Okay? and we'll assign that to x. So x will be 2. But notice that we also print out b, the string hi, and it still says hi, even though we modified it here. It's because what we're passing in is a copy. New string change is y only within the function. It has no impact on b. X and y are not copied back to the a and b after the function because they are passed by value or value parameters. Let's look at a little bit of implementation here. Alright, so here we're going to, we can actually just take this as an example. We can say, well, we'll just go ahead, start another function, cool. Int get n, which takes n as a variable, and n equals n plus 25, and we're going to return n. So, and it'll return whatever n is plus 25. So let's use some examples. If we say int y equals get n 15 or 25, it should return 50. Let's run it to make sure it's correct. And boom, it's 50. Okay? But notice that n that we passed in is a constant, so it certainly didn't change. You can't turn 25 into 50. But let's say we pass in a variable. V equals 10. Okay? And now we will count a value v. Okay, and that will return what we think. That'll return 35. Right? So if we run it, we get back 35. But in here, but now here we change n to 35. But n, if we print out n again here, or in this case v, v will be unchanged because we're passing it by value. It makes a copy, acts on the copy, and then returns the copy plus 25. Structs can be passed in as value parameters when we want to send in multiple related values. If we took our address example from the prior example, we could pass it in, and we would have the same issue though. This won't work because it should be that void shouldn't be there. Sorry. We create a new struct and we modify the first and return it backwards. Okay. So let's take an example of that. Okay, so we'll come up here and we'll define a struct person, first name and a last name. Okay, and then we'll create another method. We'll call it person because we want it to return a person. Update person, and it will take a person, which we'll call person, and what we're going to do is a simple modification to the strings in it. We'll say person first name plus equals modified and person last name plus equal modified. Now, if we return this, we'll see something funny happen. Okay, so let's take a look at that. Let's comment this out. Okay, so we'll say person equals, oops, p equals p dot, oops, first equals Larry, p dot last shown. Now what we're going to do is we'll print out what we've got. Count person equals, and we'll parameterize it just to make, parenthesize it just to make it clear that it's a structure. Or actually do this even. And then we'll print out p dot first name. And then we'll print out p dot put a comment here. Space. We'll print out p dot last name. Boom, our closing squiggle, and then we'll put a new line. Okay, so if we run this to make sure we've got, it prints the Mary shown. Now, let's call our function with this. We will say update person. Now, notice here that I am not saving the return value. So, if we print it after this, it should do nothing. Okay. So now we have a couple other options. What we could do is we could define a new person to assign it to. Equals update person P. And then we can print out P2. This time it will modify them. Now, but P would still be the same here. So one way we could actually modify P is this. We can call our function, and when it returns it, just overwrite it to P. Send in the existing value, and you'll get back the new value. And this will actually modify the underlying value. Okay? That is a simple example of pass by reference. Pass by value. So we've discussed pass by value. Now we're going to discuss pass by reference or reference parameters. Parameters can also be passed by reference. This allows the values to be changed. A value parameter makes a copy of the parameter. A reference parameter is a reference or kind of pointer to the variable. Reference parameters are specified by adding an ampersand after the type. So here, in function int simple, we're going to pass in an int reference x and an int y. Parameter x will reflect changes made in the function, y will not. A reference parameter must be bound to a variable. You can't really change 5. It doesn't make any sense. When you pass a parameter by reference, you are passing a pointer to its location, not a copy of its value. A return value, oops, I'm sorry, did I skip something here? Okay. A return value returns the results of the function to the caller. A return value is indicated by a type in the function signature. Int x returns an integer. To return a value, we always use the return statement, return x. Return always exits a function immediately and returns a value if the return type isn't void. A function that returns a non-void type must have at least one return statement. A function with no return value is indicated by return type of void. A return statement can be used with no value only when a function return type is void. A function doesn't have to return void. Doesn't have to do a return if it is void. A function often has multiple return statements, but only one is executed. For example, they're bracketed by if statements. One must be executed, though, so you've got to make sure that in every case there is a resulting return. So let's go back to by reference for a bit and take an example here. If we created a new method called update person2, and this time, instead of passing in a reference, we will pass in, a value will pass in a reference. Now, we can also just look at the returned value, at the modified value, because now we should be able to see the modifications. So, let's take this example. First, let's count out the stuff. Now, here we'll print out before person, and then we're going to call our function update person2, and we'll hand it P. And now, if we print it as the after, we should see the changes actually made to the variable. See? And that is pass by reference. Now, when you do pass by reference, you got to watch out for some things, and they're called side effects. That's why it's not always a great idea to pass things by reference and change things that way. A function which has effects outside itself has side effects. A function using cout has a side effect that it prints to the screen. Often, side effects are considered poor programming practice because it violates the black box principle. Void functions are called procedures, and they may use side effects to accomplish work. Use of global variables in a function is allowed, but it's kind of frowned upon. A global variable is a global that's not defined in the method or passed into a function or passed in. Ideally, everything a function needs should be provided by parameters or local variables or instance members in the case of a class, and should return appropriate results. Functions without side effects can be called repeatedly and return the same results. That's the big thing. These functions are said to be reentrant and useful in multi-threaded programs. So, scoping is a concept that comes into play. The area of a program where a variable is considered defined is called its scope. C++ has many different scopes. The largest scope is called the global scope and is defined outside of any program and across the entire program. A global variable is visible to all functions, including main, defined after it, and is part of the global scope. So, here we define a global variable, global garbage, and we assign it in main. It's available everywhere inside the program, inside functions, main, etc. Okay. Scoping is important as variables can have different scope or lifetime. A variable declared in a function exists only in that function. Names can be redefined in a scope that overwrite the outer scope. The smallest scope wins. So here, for example, we're going to define x as a global variable. Here, we're going to define it as a local variable. But notice here, we're going to print out x before we define it. So here, it will print x as 1, change it to 3, and print x as 3, but it's still going to stay as 1 at this level. They're two different variables. So, if we say cout x, and then we use this global variable, and here we say in x equals 2, it'll use this local variable, and here we say int y equals func x, it will use yet the third variable. Global variables should be used very sparingly or not at all. Changes to global variables can cause unintended side effects, and if multiple functions change it, you can get in some very sticky code, very cookie code. Remember, the scope closest goes from closest to furthest. Variables defined in a function overlay globals of the same name and overlay variables of an outer scope. Parameters to a function also have preference over global. So if you have a parameter x and you have a global x, the parameter will win inside that function. So there are some specialized functions. A function may represent a predicate. A predicate's a statement that returns true or false. Some examples are an is-even function. Bool is even, takes int, returns n mod 2 equals 0. So here, this part is a Boolean expression, right? N mod 2 equals 0, and so is this. String is empty, returns s equals the empty string. Functions with return values may be used anywhere a value of the return type can be used. For example, in an if statement, is even 5 is perfectly callable. We can use it in an assignment, x equals fact5 for a fact function. Nested function calls are legal and are often used. So we have for example, fact function. We're going to pass into it a square root of a number computed by a power function, and then we have the power function. It's executed from outside in. So, from inside out. So we do the POW function first, and 2 to the third is 8. So we take 8 as a result, pass that to the square root function. The square root of 8 is what, 2.7 or something like that? Yeah, something like that. And then of that, we pass it into the factorial function. In a function definition, it is appropriate to call other functions. A function can even call itself. It's a feature called recursion, which we'll come back to later. So, in C++, a function signature is also called its prototype. A prototype looks like return type, name, and a parameter list, followed by a semicolon. Function prototypes can be used to get around the must be declared before use problem. In C++, a prototype is called the function's declaration. That is, it declares the function's existence. The code inside it can be called the implementation. In C++, the two can be separate. So let me give you an example here. So we come over here, and we've got our update person function. Let's just move it to the bottom because we wrote it after the fact or something like that, right? We'll move it after main. Okay. Now, we gotta get rid of it because of the duplicates. Here, when we want to call p equals update person p, guess what? It won't compile. And the reason it won't is because we're using it before it's defined. So the way we get around that is we build what's called a for declaration using the prototype. Before we use it, usually somewhere up near the top, you define it, put semicolon after it. Now, when you're doing a prototype, you don't have to show the variable name, just the type. But now, if we run it, it'll work again. Okay? So it helps you define before use. Here, we add this declaration, technically called a for declaration, and now it just says to this code, the function is declared here, but defined later, so you have everything you need. So, in C++, we don't want to put everything in a single file. Instead, it's better to break things into logical groupings using either functions, which are good, or classes, which are better. We do this by creating special type of files called header files. If we take all the prototypes for the functions in a file and put them in a header file, we can then compile and reuse them separately. So let's create a very simple math library called easymath to demonstrate this. All right, so we're going to define a new header file over here. And we'll select the file, and we'll call it easymath.h, where h is the name of the header file. Okay, and what we're going to want to do here is we're going to create these methods: add int, subtract, multiply, divide, and module. And we're all going to take integers. So let's come back to our code here. All right. So first what we're going to do is pragma once. What this means is don't include this header file more than once. There's an old-fashioned way to do it too. You can say if not def easymath.h, which defines a preprocessor directive called easymath.h. If it's not defined, then we're going to define it. Okay, define easymath.h, and we put all our code here, and then we'd say end if, and these are preprocessor directives. Now, we put our code here, so that way it couldn't be defined more than once, but that's ugly. So they added pragma and once. It means just define it once. Now let's define our function headers. We'll say we're going to define int add, which takes int at 2 ints. We'll say int subtract, which takes 2 ints. Int multiply, which takes 2 ints. And int divide, which also takes 2 ints. And int modulus, which takes 2 ints. Okay, we've defined these functions. We haven't implemented, but we've defined them. Okay. Now, we want to implement our functions, and we're going to do this in a separate file, easymath.cpp. Okay, so we're going to create yet another file. Okay, and then what we're going to do is implement each of these functions. And now I'm just taking some shortcuts here because I'm lazy. Now for each of these functions, we're going to implement them. So get rid of semicolon, put our functions in here, with these variables names, and we'll return. Okay. Similarly, we'll do the same thing for all our other functions, and I'm going to do this quickly. Set these up. Notice I screwed this up. Now, notice for division, I'm going to implement this a little differently. And we're going to return a special value if y is 0, because we don't want to divide by 0. Now, there's a better way to do this. It's called throwing an exception. We'll come back to that. Otherwise, I'm just going to return x divided by y. And for modulus, put x and y. Return. Okay. So this is our library, easymath.cpp, that implements what we've declared in there. Now, how do we go about using them? Okay, so what we need to do in our main code is we're going to include our header file just like we include others, but this time it looks a little different because it's our own, and we got to tell it its name and where it exists. Now, notice the less than or greater than are used for system-defined header files, double quotes, and the .h are used for yours. But now we've included the function, so now what we can do, let's comment all this out. Let's comment all this out as well. So make ourselves a little cleaner. Actually, you know what we'll do? I'm going to comment out this whole function and redefine this guy out. Okay, so now come up near the top, create a new main, blah, blah, blah. Now, since we've included easymath, we can use the functions there. Int sum equals what do I call it? Add 3, 5. Okay, and let's just output this instead, or let's count equals okay, and then we can do the same with subtract. This time we'll do it in line. Okay. And we can, of course, use variables as parameters as well. X equals 25. Int y equals 3. And here we can say count, multiply. I don't know why I said subtract and not multiply. If we run it, we get exactly what we think. Now, when we use REPL IT, all we got to do is press the start button. But when we want to use the command line, we now need to tell it the names of our output executable and all the C++ files we're using. This tells the compiler to build the executable math.test.exe using the files main.cpp and easymath.cpp. The header file is included by main, so it doesn't need to be specified. And to run the app, we use /math.test.exe in Linux. So coming back here, go back to our shell, and we'll say g++-o for out, and we'll call this math.test.exe, and we're going to tell it to use the files main.cpp and easymath.cpp. Run it. It's done compiling, so now we can run our executable. There you go. It works just fine. So one way to think about programming is called stepwise refinement. It's the process of refining a process into finer and finer steps until you reach an atomic level and you can actually implement it. So for example, make toast. What are we going to do to make toast? We're going to buy bread, place bread in toaster, start toaster, remove bread, and butter bread. Now you can keep going further down. To buy bread, you have to leave the house, walk to the store, etc. But you only need to go down as far as you need to actually implement it. So this can result in actions like scrape butter off knife onto bread and so on. And that's one way to think about creating a program. We'll come to another later. So now we're going to talk briefly about recursion. A recursive function is a function that calls itself either directly or indirectly through another function. Recursive problem-solving approaches have a number of elements in common. A recursive function is called to solve a problem. The function knows how to solve only the simplest or base case. If the function is called with a base case, the function simply returns a value. If the function is called with a more complex problem, it typically divides the problem into two conceptual pieces. A piece that the function knows how to do, and a piece that it does not know how to do. This new problem looks like the original, so the function calls a copy of itself to work on a smaller problem. This is referred to a recursive call and is also called the recursion step. The recursion step usually involves a return statement because its result will be combined with the portion of the problem the function knew how to solve to form the result passed back to the original caller. The recursion step executes while the original call of the function is still open, i.e. it hasn't finished. The recursion step can result in many more such recursive calls. So we've all seen a factorial in math. N factorial is the product of n times n minus 1 times n minus 2 and so on, with n 1 factorial equal to 1 and 0 factorial equal to 1. So there are two ways we could write this. We could write this as an iterative factorial. The factorial of an integer number greater than or equal to 0 can be calculated iteratively or non-recursively by using a loop. The recursive factorial definition of factorial function is derived by observing the following algebraic relationship. N factorial equals n times n minus 1 factorial. So it's smaller. So if we took 5 factorial, the evaluation of 5 factorial will proceed as following with a succession of recursive calls until 1 is evaluated. The diagram shows the return value from each recursive call to its caller until the final value is calculated and returned. So 5 factorial comes down to, calls recursively to 5 times 4 factorial. 4 factorial calls down to 4 times 3 factorial. 3 times factorial comes down to 3 times 2 factorial. 2 times factorial of 1 equals 1. Okay, so now what we do, in the same call, we look at the returns. From this final value, 1 would be returned. So this has now become 2 times 1. And that would be 2. 2 factorial will be replaced by 2, so we get 6. 3 factorial replaced by 6, which is 24. 4 factorial would be replaced by 24. 24 times 5 is 120. So let's implement a simple program to implement factorial. All right. Well, a function to implement factorial. Let us define our function here. And to keep things simple, we're going to define our prototype here. We'll say int fact, int, right? And so we can say here int fact, int n, test our base case if n is less than or equal to 1. We're going to return 1. Otherwise, we're going to return n times fact n minus 1, which is just like the math. Okay. So now when we want to test it, let's count this stuff out here. Okay. Count. Oops. Let's try it with 10. It's going to be a much bigger number. Okay, so now we run it. And boom, there we go. And it gives us exactly what we thought. That's our first recursive function. Now, we can also, as explained here, build it non-recursively and just use a loop to sum the values times its repeating values. So we're also going to look at another recursive problem, the Fibonacci series. It begins with 0 and 1 and has the property that each subsequent Fibonacci number is the sum of the previous two. It differs in nature and describes the form of a spiral. It converges on a constant of 1.68 if you ratio successive numbers. It's been called the golden ratio or the golden mean, and it seems to be aesthetically pleasing to humans. So here's our recursive definition. It can be f of 0, fib of 0 equals 0, fib of 1 equals 1, and fib of n equals fib of n minus 1 plus fib of n minus 2. So we can once again implement it. Here we'll define our fib, we'll take an integer, and here we'll say int fib of n. And again, what we say is our two values for our base case are 0 and 1. So if n equals 0 or n equals 1, or you could just say if it's less than or equal to 1. Oh, I forgot my int here. I'm going to return n. But like I said, I don't really like this formulation. We could write it like, and I also had an error there. But, return n. Otherwise, return fib of n minus 1 plus fib of n minus 2. Now, let's write a for loop to compute the first, 10 Fibonacci numbers. Right? So, for int I equals 1, I is less than or equal to 10, I plus plus. Here we'll say count fib of, and we want to see what I is, and then we'll say equals, and then we'll call the function. All right, now let's run it and see if it works. 1, 1, 2, 3, so it's the sum of the few. 5, 8, 13, 21, 34, 55. So it works. And here, you're going to have a lot more recursive calls. So if we say Fibonacci 3, it'll return Fibonacci 2 plus Fibonacci 1. Fibonacci 2 returns Fibonacci 1 plus Fibonacci 0. Fibonacci 1 returns 1, and Fibonacci 0 returns 0. Here, Fibonacci 1 returns 1, and it'll get added upwards. Now, both iteration and recursion are based on control statements. Iteration uses a loop. Recursion uses a selection statement. Both iteration and recursion involve iteration of one form or another, with iterations explicit using a loop. Recursion achieves the reputation through repeated function calls. They are equivalent. They each involve a termination test. Iteration terminates when the loop condition fails, and recursion terminates when the base case is recognized. They are equivalent, and they could be replaced one with the other. Both gradually approach termination. Iteration modifies a counter. Recursion produces a simpler version of the problem. They can get into infinite loops. An infinite loop occurs with iteration if the loop test never becomes false. Iteration recurs in recursion if the recursion step does not reduce the problem during each recursive call. So here's an iterative version of factorial, for example. All right, we say n I is less than equal to 1, greater than equal to 1, and we're going to go down. And we're going to say result equals result times the previous version, the previous number. So it'll start at 10, and they say 10 times 9, 10 times 8, so forth, all the way down, and it'll return the result. So essentially, everything you do with recursion can be done with iteration, but is sometimes so much easier, especially in more advanced topics, to express something recursively.